Hello everyone, welcome back. So in this sections we are going to review some of the concepts we learned in a class about the regression analysis. So we are finally stepping into a modeling chapters in statistics. So there are a lot of math that we skip in the class, but at least I think this section help people to at least get an idea of how to build their first statistical model and trying to use this model to make some business insights. So to begin with these sections, we're going to first run the first two lines of the code right here for reading the data and also plotting the 3D graphs later. So let me just run this. Alright, so we are going to use a data set called advertising for today's demonstrations, and also it's the example that we use in the class notes. So the data sets can be found in the data folder and the data file called advertising.csv. So what we're going to do is to use the read_csv functions. So if you actually remember, when we reading CSV file, there is a base our functions called read.csv. The read_csv is actually coming from the tidyverse package, which is called the read_owl. But just want to expose some of these packages to you guys, so later when you reading other people's code, you won't be surprised how come it's not a dot but it's actually underscore. It's not a mistake, but it's actually a different reading programs from a different packages. Well, the advantage of this read_owl package is it reads the data into OWL and OWL Studio much faster, much more efficient comparing to the base OWL functions. But anyway, so let's just read this data and assign it to a variable called advertise. So now you can actually see I have the new data sets right here called advertise. Of course, you can actually check the data. Basically, just use the head functions, right, like we always do. So we can see the first 6 lines of the data sets. So basically this data set is a very simple but it's very representable data set on marketing business analysis. So the data set basically contains the sales of the company in different regions, and also the television's budget spent on advertising, radio budget spent on advertising, and the newspaper. So you can see how a combinations of these 3 spendings will ultimately driving the sales, right, of the company. So you can actually summarize this data sets, right? So let's try to summarize it. So the good part about this data set is that we have all the variables are actually in quantitative number. So you don't have to worry about the interpretations of the categorical variable. But if you are interested, of course, I will have the practice activity for you guys in the class to go over the interpretations of some categorical data used as a predictors. But for now, we just focus on the easy part, right? So we want to actually know what variable or features that can help us to explain the sales, right, of a company. Well, one easy way to see all the correlations, right, within this study, right, so we have basically 4 variables here. I want to know how they actually interrelated, right, so how they related to each other. So I can use the pairs function to visualize it. So the pairs function basically give you the pairs plots for all the variables in your data sets, right? So in this case, we have 4 variables. It will actually plot all the cross relationships in one single graph. So let's see how it looks like. So in this pair plots, you can see how TV, it's very, very strongly correlated with sales, right? So this plot right here basically represents how TV and sales data are plotted in a scatter plot. So it's a very obvious trend that you see here. Well, same for radio to sales. Well, not so much for newspaper to sales, right? And within each group, right? So TV to radio, well, very random. We don't see obvious trend, obviously, because, well, the company spending money on television's advertising and radio advertising might have their own specific reasons. There is no ties or any kind of relationship we should actually observe here. Well, same for TV to newspaper budget and radio to newspaper budget and so on. So the only trends that we see here is basically the 3 advertising budgets related to the sales, which is what we want to do, right, in this exercise. Well, furthermore, if you want to actually plot them individually, right, so you can actually create a little a frame to hold multiple graphs, right, in different size. That can help to compare the trends, right, within each other. So I'm going to use this function here called par. So we're basically parsing the plotting window, and we are defining the dimensions of this window, which is have 1 column, right? So we have only 1 column, but 1 row and then 3 columns. So that means I have 3 graphs basically side by each other. And how many graphs I can fit in this frame? Total of 3 per row, right? So let's just run these functions. And then I'm going to run the 3 plots right here independently. So 1, 2, and 3. So can you see they are automatically fitting into the frame that I created? So now I have a plot that's showing sales and television budget, sales and radio budget, and sales for newspaper budgets. Of course, you can actually reverse the axis, right, to basically get some intuitive idea. But here we are just trying to take a look at the relationship, right, between the 3 spending budgets compared to the sales. All right, so if you want to actually get into a little bit more in detail, right? So in terms of like numbers, right? Visualization is not actually giving you like a very good indicator whether they are correlated with each other. You can actually use the core functions here. So the COR function. So the core function basically gives you the correlation between 2 random variables, right? So or 2 columns of data. So let's say I want to see how sales actually related to television budgets. Well, the number returns here, 0.7822, basically means they are very highly correlated with each other. And it's positive, right? They're positively correlated with each other. Higher budget spent on televisions driving a higher sales. Well, how do we know it's this correlation is strong, or is it very highly correlated? We look at the number. So this correlation coefficient can range from -1 to 1. So negative number represent a negative correlation between the 2 variables. Closer to -1, which means they are very strongly negatively correlated. When the correlation coefficient is close to 1, that means the 2 variables are strongly positively correlated. If it's getting very close to 0, so what it means, it's basically the 2 variables are not very strongly correlated with each other. Well, let's take a look at radio and sales. In the graph, it was still showing us a very clear trend. So let's see how it looks like. Well, still pretty good, right? Still indicating there are they are actually very highly correlated. And then let's take a look at the newspaper. Ooh, so newspaper, it's much lower figure, right? So it's much closer to 0. Even though we can still expect to have a positive correlation between the 2 variables, but then they are not very strongly correlated with each other. Well, after checking all these statistics and plots, right, of course, the next step for us is trying to fit the model, right? So we learned how to do the simple linear regression model, and now we would like to fit this data into the model. So we are hoping that we can actually create a model line to fitting the data, right? To explain the relationship between cells with other variable. Well, since the strongest correlated variable in our data set is TV and cells, we will begin to build the first model with only a single variable here. So we call this a simple linear regression model that has only one explanatory variable. So what we're going to do is to use the LM function that it's basically represent the linear model. And we are going to first put the predictions that we want to make from the model, right? So cells is the data that we are going to see the results of, right? So we want to actually we want to explain cells, right? So what explains cells in this data? Well, we are going to use the regulate line right here to define what we want to use to explain this very important variable, cells, for the company. And we are going to try to use the television's budget spend. And then you want to put a comma. Well, after that, you want to define another argument here. So this argument basically point at one data set in your current working directory. So you call out the data set you want to use. So data is your keyword, and set it equals to advertise, which is the name of your data set right here. So let me run this, and this will assign, right? This model will assign to fit1. All right, so we can see fit1 is being stored, and there are some parameter inside that I can actually read it. And of course, you don't want to actually read it one by one. Instead, what you want to do is to basically have a better understanding of this model by printing out the summary of the models. So let me print the summary of this fitted model. And let me just enlarge the lower output console right here so we can see the whole summary. So now we have this very nice structure summary that tell us, well, what is the model specifications? What is the residuals, right? So the error terms in different quadrants. And of course, the most important part to evaluate for us at this point is to read this coefficient summary. So this coefficient summary basically tells you the hypothetical beta 0 in our equation, which is the y-intercept, and the hypothetical beta 1, which is the slope of this straight line model. So you can see the intercept is 7.03, and the slope of this model line is going to be 0.0 approximately 5, right, round up. And the next thing you want to see, of course, is to take a look at the t value or the p values. So remember, we talked about in the class how we are going to evaluate how trustable these betas are going to be. So we are going to use the test hypothesis, the t-test. So the t-test will give you a t-value to compare to the average hypothesis t-score. And the p-value will tell you how what is the probability that you are going to reject the null hypothesis, that you will be wrong. So the chance that we rejecting the null hypothesis that will be wrong, it's very, very small. So that means when we rejecting the null hypothesis, so we say, well, beta 0 is not equal to 0, right? Then we have a very, very small chance that we will be get wrong. So you always want the p-value as low as possible to prove that this beta is trustable. Well, same for the slope. So the slope also has an extremely small value of p-value, and that means this estimates right here, the beta 2, is very trustable in our model. So we can actually say that, well, these two estimates are very good estimates to fit the data. Well, another evaluations that I mentioned in the class is to check the R-square. So we have two R-square actually reported here. One is the regular multiple R-square, and the other one is the adjusted R square. Well, in the class, we might not actually going over this in detail, but then for you guys, you should know in the single variable case, when we're building a simple linear model, the R square here, it's going to be good enough to evaluate how well we are explaining the cells variations in the data. Adjusted R square is usually much more popular to use when you are building a multiple variable linear regression model, which we will go over the example later. But for now, we focus on this right here. So this model actually explains 61.19% of the variations of Y. So we can actually use this model to explain why the cells are different in different regions. Right? We are not just looking at the average of the cells overall, but adding these televisions into our model, it actually helps explain a lot more. How much more? 61.19% more comparing to the average, which is the average cells in the data sets. So that's a good sign, right? It's a much a successful improvement. So therefore, this model actually explains a lot in our data sets. And also, we can actually look at the p-value for the f-test to just kind of like check the overall fits of the data. So is the overall model actually trustable? Well, this p-value in a simple analysis case should be exactly the same as the p-value for your slope. So there is a reason to that, but of course I'm not going to go over the detail here. But just keep in mind, in a single variable case, the overall testing of the model should always equals to the slope testings. Because, well, if the slope is equal to 0, then that means, well, this model, it's not actually help explaining anything. So then the f statistics should be very, very low, close to 1, and that drive a p-value very high. So therefore, they're all interrelated to each other in a simple linear regression model case. Well, once we figure out how to interpret this result here, we would like to actually try to do something with the variable that we have in this fitted model. So one thing we can do is basically extract the coefficients from the model. So for instance, we can actually extract the intercepts from this model summary here, which is 7.032594. So all we need to do is to use the coefficient functions. You put in the model, and then you're trying to index, you extract the first item from this coefficients functions. So let's see what it looks like. So I run this, and then I want to extract the second value in the coefficients functions and save it as a slope. And now I'm trying to print this statement out and see if I can actually get the slope and the intercept values, just like in the summary table. So I'm going to print this. All right, so let's see. So we have an intercept equals to 7.033, which is exactly what we get right here, rounding up. And we get a slope, which is 0.048, which is exactly what we round up here too. So again, you can actually independently extract those summary informations by using the coefficients function here. The only thing you have to be careful is which number you want to extract. Right? You have to put in an index here to identify which number do you want to extract. Well, we talk about how we can look at the R square, right? So in the summary table, you can also actually extract just the R square from the summary table, right? So we use the summary, and then you use the $sign that indicate we want to extract only certain things from the summary table, which is the R square. So we can actually save this, assign this into R2, and then we print the statements. All right, so the R square is 0.6118, which is the R square reported again in the summary here. So except for the statistics and also the coefficients you can extract, somehow you can also calculate the confidence intervals of your slope parameter. So for example, if you want to know how wide your estimated beta 1 would be, right? So beta 1 is expected to be one value, which is the average value, what's reported in the model. But if the data change, right? So remember, there are always variations of this betas estimations. And we want to know how confident we are to trust this beta, right? So how much variation this beta could be. Now, building a 95% confidence intervals will help us to understand how wide this estimate could be in our model. So what we need to do is to use the function called conf_int, and then you put in the model that we estimated, and then you define a parameter here called level, and you put in equals to 0.95. That means, well, we want to build a 95% confidence intervals for the slope parameter. So let's see what we return. All right, so we have the intercept will range from 6.1297 to 7.9355, right, approximately. And the slope in this case will range from 0.04223 and 0.0528. So those are the basically confident in how confident we are this beta will fall into, right? Regardless how we changing the data, right? We are randomly drawing a set of data, right, and trying to put it into a model and trying to estimate it again. Well, most likely, how likely? 95% of a chance the beta 2 from this population data should actually fall into this range. So that's basically how confident we are to our beta. So that's why it's very trustable. Now, find the range of the TV budget spend in the data. And then we want to actually calculate and predict the sales based on certain values. So another very important application in linear model is it allows you to make predictions. So let me just run this range right here. As you can see in the data set, the television budget is range from 0.7, the minimum, to 296.4. So let's suppose I want to actually ask the company the following questions. What if I'm going to spend $200, right, to advertise on televisions? What would be the return sales, right, based on your model? Well, all you need to do in this case is to put this into equations, right? Remember, you have the intercept that you stored earlier, and then you plus the slope, and then whatever you want to spend. And the linear model, this linear equation, is going to return a predicted value for sales. So let me just try to run this. And I'm going to print these predictions here with the statements. So if we spend $200 on television advertisements, and at the end, what happened is we are going to expect to receive not receive, but actually to have a sales of approximately 16.54, right, sales in returns. So that's basically how we are going to make a predictions, right, with the model. So let me just fix this right here, just a little bit. So let's run this again. Okay, so it looks a little bit better in this case. All right, so now, of course, you can actually round this number, right? So if you want to round this number, right, that's totally fine. Just round it to 2 decimal point, right? That makes your statement looks a little bit cleaner. Oopsie. So missing a. parenthesis here, yes. Oopsie, unexpected symbol. But anyway, so I can actually round it outside before I put it in. But anyway, so let's just keep this print cells. Right. Okay, so now if you don't want to actually make a predictions just one by one like this, right? Defining the equation here yourself and then trying to run the predictions. Well, there is one actually cool functions in OWL that allows you to just run a line and put in those parameter to get a predictions value in return very quickly. So let me demonstrate that very quickly here. So if you use the functions predict.lm, it actually automatically run the prediction for you by defining the value you want to actually predict. So for instance, in this case, I put in the first argument here, which is the model that we fitted earlier. And then we want to define what new data we want to put in, right? What budget we want to spend for running a predictions. And then we are going to pass in the new data frame. And this data frame has only one column, one value, which is TV is the column. And then it will have a value of 200 under this column called TV. And once this value, right, this new data pass into this functions called predict.lm, it will use your model and trying to run the predictions for your value that you define in this new data set. So let's try to run this to see if we get the same number. Alright, so it returns here. So we have one predicted value returned 16.53992, which is exactly the same that we got earlier. Well, the good thing about this predict.lm function is that you don't actually do this prediction just for one value, because well, every time when we're passing in a new data, it is always going to be in a data frame format, and data frame can actually contain multiple values. So for instance, in this case, I can actually define two values to predictions. Right? So I want TV budgets to be 100 and 150. So I want to predict the sales based on this two value and run this. And now it returns. For $100 spent in televisions, I will get a sales of 11.786 in returns. And for $150 budget spent on televisions, I will get a 14.163 in returns. So isn't that great? Now, if you want to actually do a predictions, there are several things that you can also do here. So for instance, we can first build a data frame that contains three values that we want to actually run the predictions. So 80, 120, and 160. So I assign this to a variable here, and then I'm going to pass in this value a, right, which is this data frame into the new data, and I use the predict.lm functions to make a predictions and assign it to predicts. I run this, so now everything should be stored here, right? Now I'm going to combine. I'm going to combine what we defined earlier, 80, 120, and 160, with the predictions from those values, which is here that we define. So there should be three values in here. So let me combine them. And now we have a very nice predictions that we defined using the cbinds. So we have 80, and then the prediction is 10.83552. So you can actually try to make your own tables, right? So if you want to define a data frame, you can make your own table. So in this case, maybe I shouldn't use a sequence here. Instead, I use a C right here. Maybe I make a typo earlier to make a predictions of three values. And then I'm going to cbind the two, right? So now it's better, right? So now I have the three values, 80, 120, and 160. And each of them has a predictive sales here. Sorry, earlier I was mistyping. having a typo on the C functions. So I make a sequence. All right, so now I have all these predictions, right? I can print it into a very nice format table. You can actually start thinking about what more I can do. So for instance, the predict.lm function has another very interesting features that allows you to print the estimated value with confident intervals. So there is a parameter here I call intervals. So this argument will take the text. You can define what kind of interval you want to build. So in this case, I want to build a confidence interval. So you put in the word confidence, and then you put in another argument here called level. And this level is set to 95. That means, well, I want to build a 95% confident interval for my estimations. So let me try to run this line right here. So you see what it returns. The feeded values, right, the predictions, is going to be 16.5399, which is exactly the same as what we did before. Remember when we run the prediction for $200. Now, not only it returned the predicted sales, but it also give you a predictions for the lower bounds, right? So what could be vary in this prediction is all the randomness, right? So with the lower bounds, the estimated sales should at least be 16.006, and the upper bounds for this estimate should be 17.074. And this two boundary here, right? This boundary here actually define 95% of a chance your model prediction should be within this range, right? The cells that you are running should always be within this range, 95% of the time. So it's very, very confident that you can trust those numbers. But of course, if you want to be a little bit more prismatic, right? You want to be more secure. You want to build a much higher confident intervals. Well, all you need to do is to define the levels of confidence. And then this time I'm building a interval for predictions, right? So let's run this. I don't know. Yeah, there you go. So in this case, well, we are actually building a 99% confident interval, right? So the range in this case will be much wider. So you can see, well, the number here for the fitted value is still the same, but then, well, we are building a wider range. It covers from 8.035 all the way up to 25.044. So again, those are cool feature because whenever you're presenting your results to your management or whatever, right, that's going to evaluate this results, you want to let them know, well, what is the worst case scenario and what is the best case scenario. And the model tells us it's going to land on this point, right? But you still have the lower bound and the upper bound to basically have a better rational decisions to make. Again, well, I can actually plot those graphs with the predictions and with the plots here, scatter plots with cells and televisions. So this time I'm going to build a much better plots right here. So I think before I do that, well, let me just go up there and show you something. So remember earlier we defined the frames that we are trying to plot is going to be 1 by 3, right? So we have one row and 3 graphs next to each other. And here, before I'm running the plots, I want to define, we want to only have a 1:1 frame size. And then I'm going to run the plot right here. So you can see, now I have a very nice plot, a scalar plot that shows the relationship between budget spending and sales, right? Budget spending on televisions, advertisements. And we have the solid line right here that actually indicates the model fit. So this solid orange lines or dotted lines, broken lines, basically is what we are building from this linear regression model. This line is the model itself. So you can see how well it fits the data, right, in this case. And of course, you can actually have multiple and analytic part, we talk about how we can actually evaluate the residuals. So we can actually create a 2x2 graphs, and we just call out the plot functions here and plot the models. And in this case, there are some residual graphs that you can actually see for evaluating the model. So you can see how the residual is versus the fitting values. You can see the normal cubed, the residual versus the leverage data, right? How the outlier is actually affecting the residuals, and the scales locations. So those are basically part of the model evaluations, right? How those residuals are, you want to prove that the residuals are not actually related to our data, right? To any of the variable or the fitted values. All right, so the second thing we want to do today, so very quickly, so I want to actually know that having television's budgets in the model, it's going to give us a very good explanation to the variations of y. But can we do better, right? Can we actually make things a little bit better? So again, well, in the very last sections, I think in this class, we are going to cover the multiple linear regressions. Hopefully we do. But if we don't, then still, well, watch what we're doing here. So in this case, we want to actually build a linear model. And again, our predicted value is going to be cells, right? We want to explain cells in this model. And we want to still use the television budgets. But other than that, we also want to actually have another linear relationship added into our model, which is radio budget span. So we define the data we are going to use, right? Data equals to advertise. So now we are building a model with two predictors, right? With two features, two independent variables. So we're hoping radio is going to help us explain more about the variations of cells. So let's fit this model into fit2, right? Let's store that. And then, well, let's take a look at the summary before we actually jumping into the graphs. Now, the summary actually returns a very nice structured way. Right? We have the model specifications here, and we have the residuals quaternions, and of course the most important is, well, we have the estimates of the intercept, the estimate of the slope for televisions, estimate of the slope for the radio. So now, instead of looking at this problem in a 2D or two-dimensional, we are actually adding one more variable into our equations to make it a three-dimensional graph. Well, again, the interpretations of the p-value should be the same. You want the number as low as possible, right? So you don't want this p-value to be anything big. Well, by meaning of big, you don't want anything at least going over 0.05 would be bad, right? Anything less than 0.05 would be okay to accept, right? So this is extremely small number, so we're not worried too much here. And remember, we talked about how we use the R square in the simple linear regressions, which is this number here, as compared to the adjusted R square in the multiple regressions, which is in our case now. So this model here actually explains 89.62 variations of the cells in our data set, which is much, much more impressive. Earlier, remember the model with televisions only explains, well, 61 point something % of the variations of cells. But now we are actually having radios put into the model and help explain a lot more, a much better improvements. And the whole model's significance is very high because, well, the p-value is extremely small for the f-test. So that indicates, well, all the coefficients in our model, it's not equal to 0. Right? So all the coefficients are not at the same time equal to 0. At least one coefficient is non-zero. Right? So that's basically the test setup. So therefore, this p-value, it's indicating, well, we are actually in a good shape. Unless you're seeing a p-value again going over 0.05, right? If you have something that's 5% or more of a chance that you'll be wrong, then you cannot accept to reject that hypothesis. But for now, it's pretty good. All right, so those are the things that actually give you the same interpretations as the simple linear regression model, right? So we see the positive impacts from television's budget spends, and also we see the positive impacts from the radio's budget spend on sales. So those are very, very important intuitions to maybe your marketing managers or maybe to your company management to investigate whether they should spend money on these advertisements or not. All right, so again, you can actually do all the predictions just like how we did earlier, but what we want to do here is to show you how visually it looks like first. So I'm going to use a 3D plot right here, hoping that you can actually see this in a more dynamic ways. So let me just run this line of code right here. Oopsie, so let me just make this graph a little bit easier to read, so just to enlarge it. So let me just define the frame again. So we want a 1-to-1 size, right? So we want to just have one graph inside. So let's plot this, okay? So now you can see, well, this very nice 3D graphs for all the data points that actually give you the axis of television's advertisements, the radio advertisements, and also the sales, right, on the vertical axis. And I'm going to plot now this time we're not plotting a line, because when we're fitting a model in a 3-dimensional case, we are actually creating a hyperplane, right? It's like a flat sheet to fit all the data. So let's see how it looks like. All right, so that's our model, right? So this linear regression model actually creating a flat planes to fit the data in a 3-dimensional space. So you can see how well this hyperplane actually fitting the data. Well, when we're doing predictions in the model, now I'm going to give you another very quick way to do it. Right? Instead of using the predict.lm, you can also use just the basic predict functions here. The way how we do it is the same. So you put in the fitted model, and then you put in the arguments here. So let's say I want to actually create intervals, confident intervals for my predictions, and set it to a level of 99% intervals, right? Oopsie. And I'm going to run and store this into sales.heads. I mean sales underscore heads. So what I did here using the predict function here is to use all my data in the advertising data set for television budget and radio budget. I want to use all the values in the data sets and make a prediction for sales. So therefore, it will return 200 value of predictions, but I don't want to see all of them. So let's say I only want to see just the first 3 of the predictions here. So I'm going to print the heads of the predictions, sales underscore heads, and I only want 3 value returns. So let's see what the prediction looks like. So for the first observations, we have the fitted value equals to 20.5546. So how do we get this number? So if we go back to our data sets right here, so this 20.55546, it's literally coming from the fact that we are using the value 230 for televisions and 37.8 for radio budgets. And then we put it into our fitted models and calculate the predicted value. And in this case, the predicted value will be 20.5546, which is very, very close to what the actual data says here. And you can see how we have the 99% confident intervals, right? So we have the intervals range from 20.03755 to 21.7338. So again, if we don't get through the multiple regression model this semester, but at least you can see an example here that kind of demonstrates the use of this model. Well, how likely you're going to use a simple linear regression model in life? To be honest, very rarely, right? Not so much of a case you will use a simple linear regression model, because well, in the modern days, you are not lacking of data to evaluate the results. So in most cases, what you need to do is to apply this multiple linear regression model to actually help explains the variations of the predictions or the target variables, and hoping that you can actually fit the data with a correct variable used. Alright, so for now, I think we have done a very good demonstrations for doing the modeling, running the predictions, reading the summary tables of the fitted model, and also seeing it in the graphs. So in your future, I'm hoping that you can actually continue to learn how to apply these linear regression models to your future work. Right? It's very commonly people will use it, but it's not limited to just for business statistics you have to learn. Right? It could be applicable to many different studies. So hopefully you'll find this useful and continue to make progress in learning statistics to improve your competitiveness in the job markets. So this will be the last videos in the series. So I wish you guys all good luck, and I hope to see you guys later in the future. Have a good day. Bye-bye.